Hello and welcome to another lecture on differentiation. Today we shall be discussing about derivatives of implicit functions and parametric functions. Later we are going to deal up with the derivatives of higher order, that is the process of successive differentiation, and finally we shall conclude this lecture based on differentiation by discussing some numerical problems that would be based on differentiation of implicit functions, parametric functions, and finding out the derivatives of higher order. Now beginning the lecture by the derivatives of implicit function. Before finding out the derivative of an implicit function, first let us define what is an implicit function. A variable, let's say y, is said to be an implicit function of another variable x when y is expressed directly in terms of x. That is, y alone is on the left hand side of the equation and terms containing x and other constant are on the right hand side. When a relation is expressed in the form of a function which is a function of x and y is equal to 0, that is, an equation is given involving both x and y mixed up onto the both sides, then either variable is said to be implicit function of the other. Thus, if, for example, x cube plus 3x square y plus 5xy square plus y cube is equal to 0, here y is an implicit function of x or x that of y. The differentiation of this kind of function gives us the derivative of an implicit function. And the derivative of this kind of function would be more clear by considering a problem that would be dealt up in the later segment of this lecture. Next we are going to consider the derivatives of a parametric function. Now a parametric function can be defined by considering x and y which are functions of a single variable. For example, x is equal to phi t and y is equal to sigma t, and t is a variable. In such a case, x and y are said to be the parametric functions or parametric equations, and t is called the parameter. And dy by dx is given as the ratio of dy by dt and dx by dt. Thus the derivative of a parametric function with parametric functions x and y and variable t is equal to dy by dt divided by dx by dt. Next we are going to consider the derivatives of higher order. Now in this syllabus we are required to study the derivatives up to second order only. Now we consider a function f which is differentiable at a point x, then its derivative is denoted by f dash and is called the first derivative or derivative of first order of function f. And if f dash, that is derivative of first order of f, is further differentiable at the same point x, then its derivative is called the second derivative or the derivative of the second order of f at that point and is denoted by f double bar and is read as f double dash. The process of finding the derivatives of higher order greater than 1 is known as the successive differentiation. Now let us consider some numerical problems that would be based on the above discussed functions. Now here we are required to find the value of dy by dx if x is equal to a bracket theta minus sine theta and y is equal to a bracket 1 minus cos theta. Now here we can see that x and y both are functions of single variable, that is theta. Therefore, this function represent a parametric function or equation. Thus, using the derivative of parametric functions, we can easily evaluate the value of dy by dx. Now, as we have discussed earlier, that in case of a parametric function dy by dx is equal to dy by d theta divided by dx by d theta. Thus, in order to find the value of dy by dx, we need to evaluate the value of dy by d theta and dx by d theta. Thus, we have dy by d theta equal to, by differentiating x with respect to d theta, as a into 1 minus cos theta, and dy by d theta is equal to a into 0 minus of sine theta. Thus this is equal to a sine theta. Now in order to evaluate the value of dy by dx, we need to substitute the values of dy by d theta divided by dx by d theta. Thus the value of dy by dx is equal to a sine theta divided by a into 1 minus cos theta. This is equal to 2 sine theta by 2 cos theta by 2 divided by 2 sine square theta by 2. Thus we have dy by dx equal to cot theta by 2. Thus the value of dy by dx of this parametric function is equal to cot theta by 2. Next we have a problem in which we are required to find the second derivative of the given exponential function, which is equal to e to power 10 inverse of x. Now as we have discussed earlier, that in order to evaluate the value of the second derivative, the first thing to be done is to find the derivative of the first order of the given function. Thus let us consider y equal to e to power 10 inverse x. Now we differentiate this equation, which is, let's say, labeled as equation number 1. Now we differentiate y, that is equation number 1, with respect to x, and we have dy by dx equal to e to power 10 inverse x into derivative of 10 inverse x with respect to x. This is equal to e to power 10 inverse x into 1 divided by 1 plus x square, where 1 divided by 1 plus x square is the derivative of 10 inverse x. Now we differentiate the obtained derivative again with respect to x in order to obtain the second derivative of the given function. Thus, differentiating with respect to x, again we have d square y by dx square equal to, by the use of quotient rule, 1 plus x square into e to power 10 inverse x into derivative of 10 inverse x, which is equal to 1 by 1 plus x square minus e to power 10 inverse x into derivative of 1 plus x square, which is equal to 0 plus 2x whole divided by 1 plus x square to whole power 2. Now this can be further simplified and rewritten as e to power 10 inverse x into 1 minus 2x whole divided by 1 plus x square whole to power 2. Thus we have found the second derivative of the given exponential function, which was equal to e to power 10 inverse of x. Now we have another problem in which we are required to find the value of dy by dx in function 2x square minus xy plus y square plus 3y minus 4 equal to 0. Now as we can easily make out, that this function represent an implicit function. So in order to find the value of dy by dx, we need to differentiate this function with respect to x, and thus we have the differentiation of 2x square with respect to x minus d by dx of xy plus d by dx of y square plus d by dx of 3y minus d by dx of 4 equal to 0. Now we label this equation as equation number A. Now the value of d by dx of 2x square is equal to 4 x, and the derivative of xy with respect to x is evaluated as x dy by dx plus y into 1 by the use of the product rule, which is equal to x dy by dx plus y. Next we evaluate the value of y square with respect to x, which is equal to d by dy of y square into dy by dx, which is equal to 2y dy by dx. Next we evaluate the value of 3y differentiated with respect to x, which is equal to 3 into dy by dx, and the derivative of the constant term, that is 4 with respect to x, is equal to 0. Now substituting these values in equation number A, we have equation A as 4x minus bracket x dy by dx plus y bracket closed plus 2y dy by dx plus 3 dy by dx equal to 0. Or we can rewrite this equation as 4x minus y is equal to x minus 2y minus 3 into dy by dx. Or we can write dy by dx equal to 4x minus y whole divided by x minus 2y minus 3. Thus we have differentiated this implicit function, and thus the result obtained is dy by dx is equal to 4x minus y whole divided by x minus 2y minus 3. With this we conclude this lecture on differentiation, which was based on differentiation of implicit functions, parametric functions, and the method of successive differentiation.